everyone. My name is Jagadish Kumar and my teammate Sri Venkat are here to explain our project Blind but a Trained Hunter, which is autonomous target localization in constrained environments using hidden Markov models. Our objective is to build an agent, the hunter, that can locate and capture an invisible moving target, the ghost, inside a maze. We focused on three specific challenges, which is mastering uncertainty, that we can track the target using only noisy sensor data, which has a simulated 15% error rate, and the handling constraints. The maze walls blocks both physical movement and the diffusion of probabilities, and also the rational action we need because we need to combine probabilistic belief states with A-star search to make intelligent decisions. And coming to the approach, like we have used the hidden Markov models and A-star search algorithm to solve this. Now, firstly, coming to the hidden Markov models, to handle the invisibility aspect, since we can't see the ghost, we maintain a probability grid of where it might be. Now, coming to the inform search, to handle the navigation, once the HMM tells us the most likely location of the ghost, A-star calculates the shortest valid path to intercept it. Now, by development stack and simulation logic for implementation, we used Python and NumPy for efficient matrix operations to handle the probability grids. We, we also use the Pygame to visualize the agent's probability fog in real time. The environment is a 15-15 complex maze. The key constant here is our sensor. It only returns noisy colors red, orange, or green based on Manhattan distance, so we never get exact coordinates. Upon the completion of the project, it is going to deliver like interactive simulation, a playable app that visualizes the agent's internal belief state, source code, documented scripts for the HMM filter and search algorithms, and the performance analysis, a report on the agent's win rate across different maze layouts. Now coming to the probabilistic reasoning hidden Markov models, let's look deeper at the logic, and HMM is perfect for this because the true state, the ghost position, is hidden. The hunter maintains a belief state, which is essentially a heat map. We don't know exactly where the target is, so we assign a probability to every cell in the grid. And this process has two main steps. Prediction. We diffuse probability to neighboring cells because the ghost moves over time. Correction. The measurement update. We use base tool to update the grid based on the sensor reading. Cells that match the sensor color gain probability while others drops to near zero. The components of HMM. This table maps the HMM theory to our specific game components. The hidden state is the ghost true position, the observations are the sensor colors, which are red, orange, and green. The belief state is the probability heat map of the grid. And inform such A star. Once we have that MLP, which is most likely position, we switch to navigation. We use the A star search because it minimizes the path cost to the target. It uses a Manhattan distance heuristic, which fits our grid movement perfectly. Crucially, because the belief state changes every turn, A star recalculates the optimal path dynamically at every single time step. Coming to our project flow, the moves invisibly to a random neighbor. The hunter applies a diffusion model spreading uncertainty to adjacent cells. The hunter gets a noisy sensor reading. We apply Bayes' theorem to refine the map and pinpoint the ghost. The hunter identifies the probability cell, plans a path with A star, and takes a step. From now here on, my teammate Sri Venkat will continue.
I'm here to walk you through the technical implementation and the results of our AI project. So let's start at the simulation environment itself. Let's run the interface which is generated by this main.py file. This is the environment. Now you can see procedurally generated maze with a red crosshead, which is represented as the hunter, and the white ghost is our target. Now, defining the challenge of this project is that the hunter is efficiently blind and it does not have any access to the ghost coordinates like the XY coordinates. Instead, it relies entirely on a noisy distance sensor to to infer where the ghost might be. Uh, the show the ghost, this toggle will enables us to see the ghost, and see at the bottom is essentially a debug feature we added so the human can verify the AI's behavior. We have implemented the recent button, and it shows the number of turns. We can play this simulation in a single step or in auto hunt mode. So let's start with let's first reset it, and automatically the maze will get reset. Now you can see in single steps. We can also see the indicator here, and if we turn on the auto hunt, the simulation goes on itself. Yeah. So here our hunter takes like 131 turns to catch the ghost. And now moving on to code. To solve this problem of blindness, we architectured the system into three distinct modules. I want to start with the most important one, the brain, located here in HMM.py. Since we cannot observe the state directly, we implemented a hidden Markov model instead of tracking a single location. The hunter maintains a brief state, which is probably grid matching the maze dimensions. The HMM process occurs in two critical steps during every game loop. First, um, the prediction. We know the ghost moves randomly to adjacent cells, so we apply a diffusion model that takes the current probability at any given cell and spread it to the neighbors. This step is crucial because it accounts for the uncertainty of ghost's movement over time. Now, second, the update function. This is where we update, we apply Bayes theorem. The hunter receives a reading from sensor.py, which returns a color code like red, green, and orange. Now let's move on to hunter. Once the HMM has updated the probability map, the decision making logic takes over. We handle this in hunter.py. Um, Here you can see the code. And now let me run the analyze file, where finally visuals are great, but as a data scientist, we need statistical validation. We created a script called analyze.py. We created a script called analyze.py to run the simulation headless, meaning without graphics, for 100% consecutive episodes to gather performance metrics. Let me run and show it to you. Here we can see first we achieved a win rate of 99%, which is great. This is the most significant metric. It proves that despite the random movement of the ghost and the intentional noise in the sensor, our HMM successfully converges on the true state almost every single time. Second, the average steps to capture is 55.51, considering the size and complexity of the maze. This indicates that A star pathfinding is highly efficient. The hunter isn't wandering, it's hunting with purpose. Now let's move to the conclusion. We successfully demonstrated that a blind hunter can track a target without even seeing it. By combining HMM to reduce entropy and A star for efficiency, the agent converges on the true location even with imperfect data, and hence it's a smart ghost. Yeah, that's all for our project. So thank you.